All right.
All right. So the next talk is by Marcel Keller, who had probably the longest flight coming here.
No, just like 4.5 hours, 2 hours in Frankfurt from Zurich.
Okay, cool. So yeah, let's stop over in Zurich. And so we're looking very forward to learn about MP-SPDZ, a versatile framework for multi-party computation, and the stage is yours.
Thank you, Thomas. Yeah, so speaking of prototypes that shouldn't be used in production, the perfect lead to my talk. Yeah, I want to talk about my thing, which is MP-SPDZ, a versatile framework for multi-party computation. And here's the slide that you probably don't really need, but I just want to emphasize that are a lot of flavors of multi-party computation along the lines of how many parties do we trust, to what level can the dishonest party be mischievous, and also kind of less of a like security related question is what I would call the computation domain, which essentially is like, what's the mathematical domain that we live in, because you have to have that, because otherwise you can't do anything. And across all these possible choices, MP-SPDZ supports now more than 40 protocol variants. And I'm going to give you a bit of a grid. How are they distributed, about a variety of models. So in terms of like security model, I mean, you will know that there's dishonest majority versus honest majority. There's an extra line that I call like honest supermajority, which essentially is like a 2/3 majority. And the latest addition in terms of security model is the dealer model, because that's somehow becoming more popular due to the rise of function secret sharing, where essentially you have like one special party that is the dealer, not really involved in what we call the online phase, but does some pre-processing. And of course you get the period, and then of course you got the categories malicious, semi-honest, also covert, as sort of like a minor thing there. Then in the columns, we have the computation domain. So there's one column for fields that can either be computation modulo a prime, particularly like a large prime in that context, also fields of characteristic 2. Then opposed to that, we have non-field computation, which is modulo a power of 2. And the last two columns, they're about binary circuits, so like binary secret sharing based computation and gobbled circuit based computation. So yeah, over the years, like there's been something come together, and this maybe raised the question, why all in one? Why isn't it like nice to have, well, we have one framework for this and one framework for that? And I will argue, well, there's a lot of things that all these protocols have in common, and then I would argue like all general MPC has in common. So this is like explicitly not about a lot of the things that Yehuda showed, which is like a very special purpose. Oh, we want to sign ECDSA, or also like stuff related to zero knowledge proofs. But when we get into general computation, what we want to have is this black box, this arithmetic black box, where also like akin to what we had yesterday on a slide, like this what's it called, like the thing with the gloves. It's not really a glove box, because I think that's the thing in a car, but it's a thing with the gloves, where you can kind of handle things, but you can't really touch things because it will hurt you. And here is like similar. So we have this box, and the parties kind of run this box together, I mean, in an abstract sense. And then all there's values inside this box, and they want to do operations on these values, but they can't really touch the values, like only when they explicitly agree to release a value then the value comes out of the box. And of course, I mean, to populate the box in the first place, there also has to be a way in, not only a way out. And this is really like, I mean, with secret sharing protocols where this arithmetic black box is like basically always comes out in papers, it's true, but it's almost similar. You can argue this is just as true for garbled circuits. So like that's sort of like the kind of zoom out, like high level reason why, in a sense, it's all the same. But even if you like zoom in a bit, what you find out, it kind of comes down to basic operations, and like even more so, like you have the cheap operation and you have the expensive operation, and that's some sort of addition, some sort of multiplication. Like addition, like put snarkily, like every protocol worth its salt has free addition, be it free XOR in the context of garbled circuits or linear secret sharing, max, like whatever. You want addition to be free. And multiplication, well, you have to pay for that in terms of communication, computation, be it like a simple reshare protocol when you have like some basic Shamir, secret sharing based computation, like Beaver strict that we already saw, or then in the context of garbled circuits, well, usual garbled AND gates. And that kind of brings us kind of to the question, like how do we handle it, and especially in the context of secret sharing based like computation, how do we actually write this down? Because of course you want to have this in an optimal way. And if you look at this slide, like left hand side versus right hand side, it almost looks the same, but you will see that on one hand you have sequential operations, and on the other hand you have parallel operations. Namely, in on the left hand side, the first line produces a value z, which is used on the second line, whereas on the right hand side the two computations are independent. So obviously, like in a protocol sense, in the left hand side you have to compute z before you can compute u. On the right hand side you can do this in parallel. And if you think of Beaver's trick, of course that saves you communication rounds. Or if you think of Shamir's secret sharing and the resharing protocol, again, that saves you rounds. And rounds are quite expensive, because network rounds means, like, you know, you communicate with the network card of a computer, with the router, with the network card of the other computer, how many routers there are in between. So like it's very easy to amass cost with communication rounds. Now, in the way how I did this in MP-SPDZ at the low level, where you work in C++ and like whatever kind of you tell, like it's sort of like gonna happen right away. You kind of want to have an interface that allows you to do several multiplications in parallel. And I think what I came up here, like with this sort of like 4-stage interface, if you will, like I would argue that like this is sort of like the easiest way to handle this. You tell the library, okay, you want to start a new round of multiplications. These are all the input pairs, one by one. Then you tell the library, okay, now actually run all the multiplications in parallel, and then you can get all the results out. And at this stage, you cannot have a library with operator overloading, because then a multiplication would just kind of filter through to the operation right away, because at the end, you want to have the actual value. That's of course like, unless you, I mean, there's other there's other frameworks that kind of have this whole machinery in the background, like with deferred values, but I would argue that just doesn't really scale in my experience. Going up, of course, like scaling up, of course, you don't want to do this manually for larger computations, because if you have something like this, like, yeah, who wants to figure out, okay, so what can I do in parallel? What can I not do in parallel? So we want to have a way of optimizing this. And this is what the compiler in MP-SPDZ, which in large part goes back, of course, to the compiler previously in the Bristol Speed software, have. We want to specify the operations in a simple way, simple equations. This shall be the product of this and that shall be the addition of this and that and product and so on. And already like 2 lines that look relatively simple, if you have to write them out in the C++ interface that I already showed you, it's already quite a mouthful. So this is the argument to have such a compiler. And again, this is beneficial in all protocols one way or another. In secret sharing based protocols where multiplications means communication rounds, the benefit is quite obvious. In the context of garbled circuits, there is still the benefit for this AES vectorization or pipelining that has already been mentioned yesterday. Are we with time? I think I started a bit late, so I've got a bit of time left. In sort of like as a concrete example, I would sort of show you what this actually means to have this operation. So imagine you want to compute the maximum of some independent values, or put it differently, you have a matrix, you want to compute the maximum of every row. And of course, this might remind you of a max pooling operation if you have looked into machine learning. If not, doesn't matter. So the interface, Python interface, is always as easy as possible. Like you define, you want to have a matrix with this many rows, this many columns. You define an array for all the results, and then you just kind of loop through everything. But if you do this without the optimization, you're gonna call max, kind of taking the maximum out of 2 values, basically as many times as the size of the matrix, like in terms of elements. And it's only when you run this, when you run it over this optimization, that you actually get down to the number of columns. Effectively, you do compute the maximum of every row in parallel, kind of without having any extra effort to put into programming the whole thing. And that's like not the end of the line, because what we like to do in MPC to kind of reduce the number of rounds is sort of, instead of doing like trivial loops, just going loop over and over, because it's sort of inherently sequential. You want to do things in a tree-based structure, so you have like all your leaves, which are all the elements that you want to compute the maximum of, and you compute the maximum thereof in pairs, and that gives you a list that is roughly half the size and half the size and half the size. And then at the top, you have the maximum of all the input elements. And MP-SPDZ also has like kind of helpful functionality to deal with that, just like tree reduction. And that in the end, you end up with the logarithmic rounds of this maximum computation. So wrapping up this, here's a conceptual overview of how MP-SPDZ work. You can program in this Python high-level code that you saw on the last couple of slides. You run that through a compiler the compiler is also implemented in Python, and the compiler comes with a whole library with lots of functionality. It's not only this round optimization, you also have functionality to break down all sorts of computation into this essentially addition and multiplication that you're left with in many protocols, be it integer comparison, also like fractional computation, non-integer computation, all sorts of mathematical functions like exponential, sine, you name it. And of course, what I'm doing now is an increasing amount of machine learning functionality that's also implemented at this stage. Once you're done with the compilation, you have some bytecode, which is like a binary, but sort of like in a different language to your usual Intel or ARM processors. Namely, it's a binary for a specific virtual machine. And the cool thing about that approach is like you can have a very specifically optimized virtual machine for every protocol. So you can run every protocols kind of as efficiently as possible at this stage. And coming closer to the end, just I guess as an example to kind of highlight my most recent work, I have implemented neural network training in MP-SPDZ. Here's a few terms to throw around from that context. I have implemented a 4-layer convolutional network called LeNet on a data set. There's this famous MNIST data set about handwritten digits, getting to 99% accuracy after 3 times passing over the whole data, which is 60,000 examples of sort of black and white, small black and white 28 times 28 pixel grayscale images, mapping to digits from 0 to 9, running this whole thing on some collocated AWS instances. And you can see there's quite the range in terms of cost from the cheapest protocol, which is the like 3-party with 1 corruption and no malicious security, whereas on the other hand, you can also run a full threshold protocol that is based on homomorphic encryption with 10 parties, and you get a cost that is like thousands of times higher. And this already gets me to the end. Coming up to the break, the software is on GitHub. There is also a growing body of documentation on this site called Read the Docs. If you print it out, I think it's now more than 150 pages, so getting close to the length of my dissertation. Will be the next hallmark. There is the paper from CCS 2 years ago on ISCI print, and last but not least, you can follow me on Twitter, where you also find, as my last retweet, you find there a link to the postdoc positions at the University of Technology in Sydney that Sven has mentioned yesterday. And this concludes my talk. Thank you very much.
Question by you,
so I understand you write the code once and you can then run the same code for many protocols. Have you found anything surprising when you did you ever just think that one protocol would be better, but it turned out to be another protocol?
So the question is if I found any surprises along the way in comparing different protocols. Nothing that I can think of at the moment, because in the rough strokes, you know, there isn't that much of a surprise. More parties are more expensive. dishonest majority is more expensive than honest majority. Malicious security is more expensive than semi-honest security. So like that's pretty much a given. If you do something and it doesn't come out like this, you're probably doing it wrong. So no, not in particular, not that I can think of.
Christian?
For the mathematical functions and the machine learning applications, do you have like a built-in approximation stuff for like complex functions, or is that something that you just need to implement on the Python?
It's pretty much all kind of hard coded. I mean, in terms of approximation, like this functionality uses quantization, and you can you can pick your quantization parameters as a programmer, so you can play around with that, but there isn't really like that much like guidance in that regard. So you just have to pick it and run it and see how it comes out. Sort of the only magic there is like it will like automatically grow the computation domain, like depending on the parameters that you give.
Yes.
Oh, the table, yeah. No, it's gigabytes. I was like we're like, you know, like we're talking about the MPC here.
So going off you this talk, and I guess you mentioned at the beginning that this is still sort of not production level. What do you think it would take to get a framework like yours to something production level, and do you see that in the near future?
A lot. So I should repeat the question. The question is, what would it take to get it to production level? And if I foresee that in the future, yeah, no concrete plans there. I think also it's sort of like what I'm doing here is like somewhat like almost consciously against production, because I think if you go production, like you probably don't care that you can easily switch the security level. Like you want to have exactly what you want to compute in exactly the security model that you have decided on, and you want to shed sort of like the complexity that comes with such a versatile framework, because complexity means potential problems. So in a sense, I would like kind of really sort of inherent. I would say that this is sort of inherently positioned as more of a research tool. And for going to production, yeah, basically, like if you really want to base it off this, you're probably kind of gonna start by like deleting a lot of stuff, and then like having a very, very careful review of what's left.
All right, one short question by Yehuda.
Comment is one of that, but it is very useful to know what you should bother developing in production. Right? You could use this to decide what makes sense for the work.
Oh yeah, absolutely. Yeah, absolutely. I am not saying it's useless. I mean, that's not really my motivation in life. Kind of.
All right, then that's all. Thank you, Marcel, again.